in this lecture and in the next lecture, we're going to study Laplace transform. In this lecture, we're going to see a basic introduction to Laplace transform. In the next lecture, we're going to try to understand what the Laplace transform actually does. So we'll take at least 2 lectures. I will see if lecture 7, in lecture 7, if we need more examples of Laplace transform, we can take that lecture just to go over Laplace transform and perhaps some more convolution integral. But you let me know by the end of lecture 6 if you'd like 1 extra lecture on Laplace transform, or if we can move on. So I have that 1 lecture buffer in the schedule, and we can use that for lecture 7 to go over more examples of Laplace transform. If this is the first time you're seeing this, it might be useful. But for now, we have 2 lectures. In the first lecture, to be very frank, I don't expect you to fully understand what we are doing. We are going to go some basic principles of Laplace transform and see how we can use it to solve a differential equation without really understanding what that transformation is doing. Let's just accept this mathematical tool as it is, without really thinking about how it does it, which is typically not a very good strategy, but we'll get there in lecture 6. In lecture 6, once we know what the Laplace transform can do, then you're going to study how it does it, because that's very important. How does the Laplace transform solve a differential equation? So today is the basics, is just looking at a table of Laplace transform, solving differential equations using it. Lecture 6, how exactly does the Laplace transform works, and it's in more exercises on Laplace transform, and then lecture 7 will assess back then. So for today's lecture, I need you to have the lecture slides and also this table of Laplace transforms that I posted on Brightspace. Please download it and have this with you. It's posted under lecture 5. This is called table of Laplace transforms. Okay, so by the end of this lecture, the idea is to focus is that you understand the principles of Laplace transform, use the forward and inverse Laplace transform for basic problems, and use it to solve a differential equation. Here is a supplementary video that I encourage you to watch later. Is a lecture that I recorded on Laplace transform. There are more examples after our lectures if you still have some trouble. Here is a good video to watch that was recorded here in this room. So why are we dealing with Laplace transform? What is the point of bringing Laplace transform? Well, that's a tool that we're going to use to solve differential equations. Let's consider this mass spring damper system here. And if you apply here, we stretch the spring by 5 millimeters, hold it, and then release it at time 0. How does the position of mass 1 evolve over time? If you want to answer that question, we need to derive a model. This model will be a set of differential equations with first and second derivative of position. We have 2 sets of equations, 1 for each mass. And then somehow, if you want now to relate the input x to the displacement of each mass, we have to combine these 2 equations, get one equation, and then solve for that differential equation. Now, the problem of combining these equations is that we have variables that are depending on their derivatives. How exactly are we going to combine everything to just be a function of either mass 1 or mass 2? We could use analytical tools you learned in differential equations, but that will make our problem a lot more complicated. That's where Laplace transform comes in, because it will transform these derivatives into a common variable, the Laplace variable, and that will allow us to manipulate these equations very easily and also find the solution to the resulting equation. Here is another example. If you have this robot arm and we apply a torque to one joint of this robot arm, how can we calculate its desired output? Or we can do the other way around. If we want the robot to follow a specific speed or a specific trajectory, what are the torques we need to apply to each joint to make the robot follow that trajectory? Well, to do that, we need the same sort of model. We need a function that describes the behavior of the robot. We give it an input, we watch the outputs, and you can invert the model now to find the optimal inputs to give the desired trajectory. And in that process, we're giving inputs to the system and solve the resulting differential equations. And the way you're going to do that is through the Laplace transform. Okay, so ultimately what we want to do is to calculate the output of a system. Consider here the mass spring damper system. If we model the relation between force and displacement in this mass spring damper system, we'll have a model such as this one, mx double dot plus bx plus kx. Now, you notice here that there are x is the displacement, and you have the first and second derivative of it. If you apply a force to the system, every time we apply a force to the system, we need to solve for that differential equation to calculate the function x of t. This might be a bit complicated to do analytically, because if the input changes, the whole system, the whole differential equation will change, and every time you have to solve for a new system of differential equations. Using the principle of convolution that we saw before and the Laplace transform, this will become a model that is a function of this new variable that you're going to call the Laplace variable s. We'll see how to get there. This model doesn't change. And when we apply an input force to the system, we can simply multiply them together and find the resulting transformation and the inverse transformation to find x of t. So this will work regardless of the type of input we have. And now we can change the input to the system and calculate the output through the exact same process. So that's why we need the Laplace transform. Now, what exactly is the Laplace transform? For now, we can simply assume that it's a way to solve differential equations. We'll see how it works in the next lecture. In this lecture, let's just focus on how we apply it without really focusing on how it does it. So the idea is simple. We have a time domain function that we have here. That's the mass spring damper system model. We'll take the Laplace transform of this system, which converts the function into a function of s, and s is the Laplace variable. And you see now that all the derivatives disappeared. This polynomial that we got inside here is simply a function of s, the Laplace variable. And you see the derivatives are gone. And following the same procedure, we can do the inverse Laplace to go back to time domain. And when you go back to the time domain, we can find x of t as the solution of that differential equation we started with. So the used Laplace transform will always involve three steps. Find the differential equations that describe the system of interest, find the Laplace transform of the differential equation, and then find the inverse Laplace transform to solve for the differential equation in question. Here is the definition of the Laplace transform, mathematical definition. This is not going to make a lot of sense now. Hopefully it will make more sense in the next lecture, but here it is regardless. So the Laplace transform of any signal is defined by this integration. Integral from 0 to infinity of the function we are, or the model we are taking the Laplace transform of, times exponential of minus s times t. Now, what does this element here mean? We are taking the function of interest, multiplying that by exponential of minus st, taking the integral of it. What exactly are we doing? Well, that's the focus of lecture 6 once again. But as a brief introduction here, we can say that this function, that this variable s is a complex variable, and this complex variable has two components. One that is real and one that is imaginary. So if data has two components, we can see that by replacing exponential of minus st with those components, negative sigma plus j omega times t, we can write this as an exponential of negative sigma t, exponential of negative j omega t. This is a real number. It's an exponential waveform. And this is a sinusoidal waveform, sine of omega t minus j cosine of omega t. So what are we doing here? This signal, this exponential of negative s of t has two components. One component that corresponds to exponential waveforms, and another component that corresponds to sinusoidal waveforms. And that is very interesting because the solutions to any differential equation can only be exponential or sinusoidal. It cannot be anything else. Why? Because when you take the derivative of a sinusoidal or an exponential waveform, they are still exponential or sinusoidal waveforms. They don't change shape. Those are the only functions that when taking the derivative of, the response is always the same shape. The derivative of an exponential is an exponential scaled with a gain, with a constant. The derivative of a sine waveform is a cosine waveform, is scaled up or down and shifted in time with a phase shift, but the shape doesn't change. So if you take, for example, these differential equations that I have here, or any differential equation, those are the only two possible solutions: exponential, sinusoidal, or of course a combination of exponential and sinusoidal. That explains why this component of this transformation here has both a sinusoidal and a exponential component, because those are the only possible solutions of those differential equations. Now, what are we actually doing here by multiplying these two functions together and taking the integral? Well, we are decomposing the differential equation into exponential and sinusoidal waveforms that best match the components, the components of its time response. For example, in the mass spring damper system, we can see the mass raising exponentially and reaching a certain value. We can see that oscillating before it reaches a certain value. This differential equation will highlight those components that will make up for the output of the system, for the solution of the differential equation. Are they sinusoidal, are they exponential, or are they a combination of them? That can be seen through the transformation. So what is exactly this transformation doing? It is taking a function, converting that into the Laplace domain, and in the Laplace domain, we now have information about the exponential and sinusoidal components that solve that differential equation. That's exactly what the transformation is doing. It's very abstract at this point. I understand that. We'll go back here in lecture 6 and see exactly what that means. But for now, that's enough. And for now, we can simply use the Laplace transform, convert the signals into this S domain that are now decomposing the sinusoidal and exponential components of the solutions. Do the inverse Laplace transform to go back to time domain. So before we start that, here are two important notations here. Lower cases will denote time domain signals, uppercase denotes frequency domain signals. So the function f of t, when you take the Laplace of the function f of t, that will become capital F of s. And when you take the inverse Laplace of f of s, we go back to f of t. Okay. So here is what I was explaining earlier. Assuming that the solution to our differential equation is this, we can recreate that signal using a combination of sinusoidal waveforms and exponential waveforms, because again, those are the only possible solutions to any differential equation. By decomposing the signal into its sinusoidal components and exponential components, we multiply all these guys together and we convert the function from time domain to a new domain that we're going to call here the complex domain or the Laplace domain. And that is not in time anymore. We are now dealing with the frequency. Instead of describing systems in the time domain, how they behave over time, we are describing now how they behave over frequencies, depending on the frequency of the input, the frequency of the sinusoidal components that make up the signal x of t. Now, let's take one signal here and take the Laplace transform of it. So here we have a function of t that is simply exponential of t. And you want to find the Laplace transform of this function. Well, if the function is f of t, when you take the Laplace transform, you're going to get f of s. Here's the definition of the Laplace transform. We can simply replace f of t with the signal we want to take the Laplace transform of, that is exponential of t, exponential of negative st dt, which is the same as exponential from 0 to infinity of e t minus st dt. This is the same as exponential from 0 to infinity of e, let me see the easiest way, okay, let's do it that way, t 1 minus s dt. What is the result of this integration here? One over 1 minus s exponential, and now this goes from 0 to infinity. We can take the limit of this function when time tends to infinity, and we can also take the limit, replace 0 in the function. And if you solve for all that, this is just math steps, it's going to be 1 over s minus 1. Right? We could, for example, just do it with a negative sign here, plus, and then we can see that when time tends to infinity, I think this is easier to see, time tends to infinity, exponential of negative infinity is 0. So we have 0, oops, and as of course it becomes negative. If you do the negative sign there, it becomes 0 minus exponential of 0 is 1. So that's what we get there. Right. Let's do another one. Let's find the Laplace transform of 1. Well, that's easy. Laplace transform of 1 is simply the integral of 0 to infinity of 1 exponential of minus st dt. What we get here, we have minus 1 over s exponential of negative st from 0 to infinity. When t is infinity, we have exponential of negative infinity, that's 0. And when we have 0, we have minus 1 over s, exponential of 0. The exponential of 0 is 1. This is 1 over s. So that's how we would calculate the Laplace transform. We can put any signal here, and that will give us Laplace transform as a function of this new variable s. Luckily, we don't have to do this for every function. Somebody has done it for us. And that's where this table of Laplace transform will come in handy. Here are a list of functions and their respective Laplace transforms. Impulse function, for example, Laplace transform is simply 1. Step function, 1 over s. Exponential of negative at, 1 over s plus a, which we just did. And so on. These are all functions here. And we can look at the table that I posted. This table has many different functions. You see in the first column, we have the time domain signal. The second column, we have the corresponding Laplace transform of that signal. So this table is very important. You need to get acquainted with this. We're going to use this extensively from now on. So I recommend that you stick with this table, because when you get to exams, you can print this and use this as a reference. That will be provided if you write exams in person. Okay, so here we have time domain on one end, frequency domain on the other end. Here are some functions in the slides here, but the table is more comprehensive. It will help us a lot. So let me now explain what happens when you have differentiation and integration. And this is one of the main advantages of using the Laplace transform, is the ability to convert integrals and derivatives to functions of s. And you can see the advantage of that, because now instead of having second derivative plus first derivative, we have a function of s and another function of s. We can combine them, but we can't combine first and second derivatives together. So if you take the Laplace transform of a derivative, we'll simply get the operator s, the variable s. So for any derivative, the operator, the transformation becomes s times that function. So if you are dealing with a function, for example, dx of t dt, the Laplace transform of this is the Laplace transform of the signal x of t times s is the function x of t in the Laplace domain, that is x of s, times s. If you're dealing with the second derivative, then we have x of s times s is the first derivative, times another s is the second derivative. Every time you multiply the function by s, that corresponds to the derivative with respect to time. Okay? And you can do also the same to integrate a function. If you take now the integral of function f of t, for example, the integral is simply the function f of s, which is the Laplace transform of s of t, divided by s. If you take the double integral, then we multiply that by 1 over s again. And that is now the double integral of f of t, 1 over s squared. Okay, so we can see the Laplace variable as the differential of operator. Every time we multiply a function by it, we are taking the derivative of that function. Every time we divide the function by that operator, we are integrating that function. Now there is important consideration here is to deal with initial values, initial conditions. For example, if you go back to the mass spring damper system and you apply a force to one of the masses, but one of the masses at the time we apply a force has a given speed, or has a given, or one of the springs is already stretched by a certain amount, those are initial conditions of the system. At time 0, there already exists a speed or a displacement, and those, of course, must be taken into account in order to find the response of that system. And here is how we are going to include them. Here is the generic expression for any derivative. You see that these new terms that show up here are all initial conditions. All initial conditions. So let me start with the first derivative just to make things simple. Let's assume that we are taking the derivative of f of t dt. And let's assume, for example, that f of t was the displacement in a mass spring damper system. Was the displacement in a mass spring damper system. The Laplace transform of the derivative is s times the function, but now for a function of s. And to account for an initial condition, we need to subtract that initial condition from the system, minus f of 0. What does that mean? Well, if f of t is the displacement of a mass, then df dt is the speed of that mass, of course. So now this corresponds to the speed, minus the function at time 0. The function at time 0, the value of the function at time 0. In this particular case, it would represent the displacement at time 0 of the mass, the displacement at time 0, if f of t is the displacement of the mass. Let's assume that we are dealing with the second derivative instead. Here's the second derivative. So we now have f of s times s times s. Each s corresponds to one derivative. And now we have two terms showing up. We have s times f of 0 minus f dot at 0. What is f of 0 again? F of 0, if f of t is the displacement, f of 0 is the displacement at time 0. At time equals to 0. And what is f dot of 0? Any ideas? What is f dot of 0? If f of 0, if f is the speed, then f is the displacement, and then f dot is the speed. So f dot at 0 is the speed at time 0. Okay, this way we can account for these initial conditions in the system that already exist before we intervene with an external force to make it change state. We'll do an example, 2 examples, and hopefully that will clear up some confusion here. But this is very important. I would add this to the table of Laplace transforms. So that's going from time domain to frequency domain. We are converting differential equations into these functions of S to be able to solve them. But that doesn't really answer our question. What we want is the response of the system in the time domain, what we can call the temporal response of the system. So to do that, we need to go back to time domain. And to go back to time domain, we need to do the inverse Laplace transform, which is given by equation 10, is simply the inverse of equation 9. 9 is what we call the forward Laplace transform. And the inverse Laplace transform, we just invert that model and go back to the time domain. You see now that the input is a function of S, and the output is a function of t. We don't need to do this manually. We can go back to our table of Laplace transforms and now just do the opposite operation. When you are in the S domain, we go back to the time domain. Okay. Let's do an example. Before I'll go there, actually, let me ask you if you have any questions. Anything at all that you would like to ask? I know that there's a lot of information. I know that this is confusing. We are going to reiterate this in the next lecture and maybe even the lecture after that. And they're going to do an example, hopefully that will help clarify things. If you don't get it, all I'm talking about now, don't worry. I'm really not expecting you to just understand this all of a sudden, because this is very, very abstract. Regardless, are there any questions? Any question is a valid question. There are no stupid questions. All there are good questions. Anybody has a question? No? All right. Yeah. Yep. Heard some noise.
Excuse me, Professor. How did you get the limits for the inverse Laplace transform?
Yeah, so the limits are the limits. What we need to go back to we need to go to lecture 6 to get that, because the function of t is defined over an entire range of over time 0 to time infinity. Then the forward we have to account for. I'm trying to explain this without jumping too much ahead, and is a bit hard. But if a signal exists from time 0 to infinity, then you need to decompose that signal within that time limit, which is from 0 to infinity. You need to analyze the signal over the range of time it exists. Right? That's for equation 9. And if you go back to equation, if you go to equation 10, now you notice that in equation 9, we are dealing with time, right? So if signal exists in time, we do the integration over a range of time. But now when we have done the Laplace transform, we move to the frequency domain. So you're not dealing with time anymore. The signal exists as a combination of frequencies and a combination of exponential components. Now you notice that the limits of the integration here have changed. It's tau plus j infinity, or tau plus j omega. Omega is the frequency where the signal exists, and that is going from negative infinity to infinity. Right? Because the first one is time, we do the entire time domain. The second one is frequency, we do the integration over all possible range of frequencies. Okay. But we'll see exactly what we are doing here better in the next lecture. Any other questions?
Hi, Professor.
Hi.
Could you go over the last slide again? I didn't really understand why we were subtracting f of 0.
Right. Okay. Yeah, so let's assume here, for example, that we are dealing with a mass spring damper system like that. And this is, we are applying a force to this system and we are watching the displacement. Let's call the displacement F of t. Okay. If we, let's assume, well, we know what to do here. If we apply, if everything is at rest and we apply a force, we know how much the mass is going to move. It's going to start from rest and it's going to start moving. But what if the mass is already moving when we apply that force? How does that information, where does that information show? Or what if the spring is already stretched or compressed when we apply the force? Where does that information show? It would be lost if we only have the first term here. Because the first term is only giving us position, f of s is position, so s times f of s is the speed, f squared times s of f is acceleration. The transformation is only indicating position, speed, and acceleration. These initial conditions that already exist in the system, that are already established before we apply the force, are nowhere. And that's where they, and that's why they show up here. They show up here as a condition that already exists before we intervene with our displace or with our force or displacement f of s.
That makes sense.
Okay.
Thank you.
I'll do an example next and we'll see how that will help. Any other questions?
Professor, what does the value of S depend on?
The value of S is a complex variable. It will depend on two terms, sigma and j omega. Sigma, you see here, is a real number, which will give us the exponential components that will make up for the solution of the differential equation. Omega is the frequency of potential oscillations of the sinusoidal components that will make up that signal. And when we add them up, we now have combinations of exponential and sinusoidal components. For me to answer that question precisely right now, it would require the next lecture. But for now, it is important to understand simply that S decomposes a signal into exponential and sinusoidal components. And when we play with sigma and omega, we can go from signals that are purely exponential, signals that are purely sinusoidal, or signals that are sinusoidal and exponential. For example, that you see here a exponential that decays over time, and you see a sine wave form within those limits. We can make any signal that is either exponential, sinusoidal, or exponential and sinusoidal by changing sigma, the values of sigma and omega. Okay, and this is pretty good because we know that the solutions to any differential equations can only be of this type. Okay, but we'll get into this into more details in lecture 6. I know how frustrating it is when you know just showing you equations over equations and not telling you exactly what they do and just asking you to accept them as they are. I don't like that, but we have to do it this way. Next lecture, we are going to see in more details what exactly this is doing. Okay. Any other questions, folks? Yep. Any other questions? No? All right, so let's do an example. You have this example here in this slide and the next one. I'm going to use a light board, so just to change things a bit, but you can use your 2 slides there too. What's going on there? Yeah, okay. So here we have a simple electrical system. We have a RL system. And the question says that at time 0, there is a current through the inductor. Let's call that IL, or the current through the inductor is I0. At time 0, there exists a current through the inductor that is there in the form of electrical energy, and that magnetic energy, excuse me, and that current exists. Now we want to see how the system responds to that current existing here when we apply 0 volts to the system and just let it go. So let's assume, for example, what we did here was we charged this capacity, we turned on this voltage source. This voltage source established a current in the loop. We cut off the voltage. Now this is just a short circuit here. The voltage potential is 0, and you want to see what happened to the current that was established here. The current will loop and eventually dissipate the energy from the inductor in the resistor. We want to find this value of I of t. Okay, so how do we do that? Well, we need to first create the model. That's the step 1 to solve this problem. What is now the relation between I and V for this loop in the time domain? Give me the equation for that. V, I'll do the hardest part here. V of t equals, that's it, now it's your turn. Yep. Sum of all voltages across these in this loop. What is it?
Would it be IO times R?
I times
Or R?
I of t, right? Current times the resistance, that is the voltage drop here, plus the voltage drop across the inductor. What is that? Plus voltage drop across the inductor. Anybody?
It's L di dt.
Excellent. L di of t dt. Okay. Very good. So that's the equation that describes the behavior of the system. Now we turned on the system. The current was created here. The current loaded this inductor. There is a current I0, and then we turned off the input. When you turn off the input, this becomes 0. Now, if you want to solve for this differential equation, we could do that in the traditional way. This is a very simple one, but let's complicate things and do the Laplace transform. So now, second step is to take the Laplace transform of this function. Well, 0 is what I apply to the input. 0 is 0. Right? The Laplace transform of a constant is the constant itself. The Laplace transform of a function, I of t, as we saw, becomes simply I of s. And function Laplace transform of L is L. And now we have the Laplace transform of the derivative of the current, the derivative of the current. What is that? The derivative of the current. Now we need to go back to this here. We know that the derivative will now take the form of the Laplace operator. Here we have the first derivative only, so we are dealing with this equation. S times the function itself minus the initial condition of that function. Let me write it here, and then I'm going to open the, so the, okay. Actually, let's not do it. So what goes inside here? This is the Laplace transform of di dt. The Laplace transform of the derivative is simply s times I of t, which becomes I of s. We see di dt, I of t becomes I of s, and the derivative becomes s. What is missing? What is missing? Let's go back here. We did the first term that is circled in red. The second term, it states that we need to subtract the initial condition from the function f of s. What initial condition exists here? Well, the initial condition is the initial current, which turns out to be the current that already exists in the inductor. So this is minus would be I of 0. And I of 0, we call that I0. Or the current when time equals to 0. Okay, are we good? Any questions here? No? Okay, so now we have all functions of S. Notice now the derivative disappeared. And because the derivative is gone, you have simply functions of S. That will make our job a lot easier because you can now combine these terms. We couldn't combine this I of t with di dt. But now we can because you have I of S here, we have I of S there, and you just have this variable S that you can treat as any other variable. So what you can do is to multiply this out, move to this side anything that has doesn't have I of S, and keep on the other side things that have I of S. So L times I negative I0, move this to the side is Li0. And on the other side, we have I of S that multiplies R and multiplies L times S. We can now create an expression for I of S, which is Li0 divided by R plus Ls. I can divide both the top and the bottom by L. We have I0 divided by S plus R over L. Okay, that's now the expression for the current I of t, but in the frequency domain I of S. What do we do with this? Well, this is really not of much use because this is a function of the frequency. This is a function of the Laplace variable. That's not what we want. What we want is I of t. What we want is I of t. So to find I of t, we need to find the inverse Laplace transform of this function. And that's where we can go to the tables now. Let's go to the table of Laplace transform and see which property in that table we can use to solve for this. Let me just reopen my PDF here because my iPad is acting. Okay, so let's go here and look at which property we can use in this table. You have the table with you. I'm going to keep the board on here and look at the type of equation you have here. Tell me which property in the table we could use that will resemble, that falls in this format that we can use to solve for the inverse Laplace transform. You have the table with you. We see that we see here equation 2, or property number 2. I'm going to write this on the board here. We know that the Laplace transform of EAT equals to 1 over S minus A. That's number 2 in the list. Exponential of AT equals to 1 over S minus A. See what we have here is a constant. Well, there's a constant there, so we don't care. I0 is a constant. We have S plus a constant. So this is clearly falling into this category. All we need to do is to identify the value of A. What is A? Well, S is here. That matches. A is negative. A is R over L. So A is negative R over L. What is the inverse Laplace now? Well, if you look at this, this was I of S. Now it becomes I of t. And we have identified A. A is negative R over L. I0 is a constant. So we only take the inverse Laplace that is the same constant as we did. R here was R. The inverse is still R. And this part becomes exponential of negative of A times T. A is negative R over L T. And this is the equation that describes the current in the circuit as we let it go from 0 voltage. It simply decays exponentially to 0. That makes perfect sense. Now this is the solution to this differential equation when V is 0. We input it in here, it will satisfy the equation. Any questions? Any questions? You can ask whatever. Anything is not clear, just ask. Is everything good? Does nothing make sense? What is going on? If I have no feedback, I'll keep going. So here we did the 3 steps. We created a model. We took the Laplace transform of that model. We took the inverse Laplace transform, and by doing that, we found the solution of the original differential equation. We'll do more examples as we go. Are there any questions? No? All good? All clear? Excellent. Okay, so let's go back. So here are some properties of the Laplace transform that we already applied. The Laplace transform is linear. It will satisfy the 2 conditions for linearity. The Laplace transform can also, if there is a time shift in the Laplace transform, we can in the input signal, we can compensate for that in the Laplace transform. The time shift also applies to the Laplace transform. You see simply here that when the signal is shifted in time, as we did for the convolution, was shifted by this amount of tau, we can simply add this new term that will compensate for that delay. And the last property is the convolution. Instead of solving for the convolution integral as we did in lecture 2, all we can do here is to multiply 2 signals and then take and that is equivalent of convoluting those 2 signals, which make things a lot easier to solve for. For example, if here we had in this circuit, we were dealing with an input voltage that was a step input. We have the model. The model will give us the impulse response. We can multiply that model with the input, and that is the same as taking the convolution of the 2 signals. That is the same as taking the convolution of the 2 signals without having to do that crazy integration over graphical integration. So this property we're going to use most of the time. So just keep that in mind. And when you multiply 2 signals in the Laplace domain, what you're actually doing is that we are taking the convolution of them. Okay. Here are the Laplace transform of our favorite input signals. If you take the Laplace transform of a delta signal with a magnitude of A in the frequency domain, that is simply A. If you take a step function of magnitude A and take the Laplace transform, that is A over S. If you take a ramp function, the ramp function is the integral of that, isn't it? So what do? We multiply that at 1 over S. And that is the ramp function. Parabolic function is the integral of the ramp. So if you take the ramp and multiply that by 1 over S, we have the parabolic function in the frequency domain. Most of the time, we'll be using the first 3. So a step function becomes the magnitude of the step divided by S, ramp function divided by S squared. And if it's an impulse, it's simply the value of that impulse. Okay, we'll come back to the signals all the time. Let's do more exercises now. Let's do exercise 1, and I'll try to fit as many exercises as we can here. So let me erase the light board, and in the meantime, I'll let you look at these functions, function g, f, g, h, and y, and you want to take the forward Laplace transform of them. So these are very simple functions because you'll find them in the table of Laplace transforms that I posted. So what we can do now, as I erase the light board, is to find the corresponding function in the table and then try to take the Laplace transform, identify all the variables there, and try to take the Laplace transform. So go ahead and take the table and try to find the corresponding value in the table, the corresponding transformation in the table. As I clean here whiteboard. This is the disadvantage of the whiteboard. Okay, 1 more second. Almost there. Okay, so to solve this, we'll need both the table and the equations, of course. So have the table with you. Otherwise, this will make little sense. Okay, so the first equation that we have is sine of 3t, 2 sine of 3t plus 5t. So the first one is simply a sine of 3t. So if you go to the table I shared with you, where is that in the table? Is number 7. Number 7 says that the Laplace transform of sine of at is a over s squared plus a squared. A over s squared. A over s squared plus a squared. So what is the Laplace transform of this function? Well, f of t becomes f of s. 2 is 2, that doesn't change, it's a constant. Now sine of 3t becomes this, so what should I write here? A is 3, so this becomes 3 over s squared plus 9. 3 over s squared plus 9. Okay. Yeah. Okay. Now we have this term plus 5t. Which property can you use to take the Laplace transform of that? We can use number 3. Number 3 states that the Laplace transform of t to the power of n is equal to n factorial divided by Sn plus 1. So 5 is 5, that doesn't change. T is to the power of 1, so n equals to 1. 1 factorial is 1. S times n to the power of n plus 1 is s squared. All right, this is the Laplace transform of that function. Any questions? Any questions? Now, let's do one more then. Function g of t is exponential of 3t plus 10. So we have two terms, exponential and that. If you go to the table, which one can you use to solve for the first term? Well, we can use number 2. Number 2 states that the exponential of at equals to 1 over s minus a. That's number 2. So what is the Laplace transform of exponential of 3t? Come on, folks. I don't see the chat, so you need to open your mic. A is 3, so you have 1 over s minus 3. This is g of t, so this is capital G of s. Plus 10. 10 now, because it does a multiple, 10 by itself is a impulse function. Is a step function. Is a step function. It doesn't multiply this variable. Is not scaling up. This is acting as a forcing term. Is acting as a step to the system, so that it would be number 1, 10 over s. So this comes from number 1. All right. Any questions? No? All right. So let's do h of t. Next one is h of t. Let me just clean the light board here. And you're going to do that. And then you do an example with a mass spring damper system. Try to put something more concrete, have something a bit more tangible. Let's do h of t. I will share here the excuse me that. So take a look at g of t, h of t. Excuse me. Let's try to calculate that one. See which property in the table can be used for that. Let me write it here. H of t is 10 exponential of negative 2t sine of t plus 5 exponential of negative 2t cosine of t. Which property works here? We can look at number 19 and number 20. This one you can take from number 19, which says that the exponential of at sine of bt is b s minus a squared plus b squared. And we can take number 20, which says that the exponential of at cosine of bt is s minus a over s minus a squared plus b squared. What is a? A is negative 2. A is negative 2 here, b is 1. This side here, a is also negative 1, b is also 1. So h of s becomes capital A, h of t becomes capital H of s. 10 multiplies, scales that function, so it's still 10. So this portion here, exponential of negative 2t sine of t becomes b, which is 1. S minus a is negative 2, so negative a is plus 2, is squared plus b squared, which is 1 squared. And plus the second function, 5 over s minus a. A is negative 2. A is negative 2. So s minus 2 is s plus 2. Same downstairs here, s plus 2 squared plus b squared. B is 1 plus 1 squared. Okay, so this becomes s squared plus 4s plus 5 in the denominator, and the numerator is as stands. Any questions? So the process here is always the same. It's always the same. I promised that I would not go over time today myself. We'll see if that holds. But if I do, feel free to leave when a time is up. These will be recorded and posted anyways, and at least you have it in the video. Any questions, folks? Yes, no? You're very quiet today. That's why I like in-person classes better. At least they don't have to stare at a screen all the time. All good? Okay, we can do inverse Laplace in the next lecture. The inverse will be the exact same, but now we are here and you're going to go back there. Right, so we just need to look at wherever resembles the function in the table. So let's do, I want to do this example here as I clean up the board. In this example, we have a mass spring system, and the problem says the mass is released from rest when the spring is stretched by alpha units. Calculate the position of the spring, of the mass as a function of time. So that's two important statements in this problem. The first one is the mass is released from rest. What does that mean? It means that when time is 0, it's not moving. It's at the initial speed is 0. The second important statement here is that it is released when the spring is stretched by alpha. So from the first one, if you're dealing with this mass spring damper system and y is the displacement, the problem says release from rest. This means that y dot at 0, the speed at time 0 is 0. The second portion of the statement says that y0 is alpha. The spring is stretched by alpha units when time is 0, and then we basically are stretching the mass and just letting it go. I want to calculate the response of that system. So let's do that. Here is the mass spring damper system. First step first, we can calculate the equations. For that, we need a free body diagram. Remember that the mass is moved towards me, the spring is stretched, and then we let it go. So the spring is pulling the mass back, and the magnitude of that force is k times the displacement y of t. K times the displacement y of t. And that's the only force acting on the mass. That's it. So you can now do all sum of forces, assuming that I'm moving in the other direction is positive. We have negative ky of t equals to my of t double dot. All forces, mass times acceleration. So my double dot plus ky equals to 0. And that's the equation of motion for this mass spring damper system. Mass spring system, there is no damper, right? If we had friction between this and the ground, then another term would show up here, which would depend on y dot. Well, for now, that's the equation of motion. This is basic from lecture 3. Now we need to, what we want to is actually the response of the system y of t as we stretch the mass and let it go. By doing that, we stretch the spring, we are holding a constant, the speed is 0. So we can tell that, we can say that y dot at 0 is 0. And because you're stretching the spring by a factor of alpha, y at 0 is equal to alpha, that amount of stretch we're giving before we let it go. And this is the equation of motion. Now let's take the Laplace transform of this to find the corresponding equation in the Laplace domain. So the first term, I'm going to write this one in red. Can you see this color? Yeah. In this color here, the Laplace transform of that. What is that going to be? It's going to be m, which is a constant, times the Laplace transform of the second derivative of y. Second derivative of y. So tell me what happens in here. If you go back to the table, to the slide that shows that, we are now here and we are dealing with the second derivative. So we need to account for this initial condition. So we have these three terms to account for. S squared f of s minus sf0 minus f dot. That's 0. So what it is, tell me what goes inside that bracket there. What goes inside the bracket? We have three terms. The first term is the second derivative of y. The first derivative would be y of s times s. Second derivative is s squared times y of s. Right? At y double dot s squared times y of s. Minus, we need here s times y of 0 minus y dot at 0. So that is for this term. Now we have this term here, which is simply k y of t becomes capital Y of s, and this is equal to 0. Sy of s, we know y of 0 here. Y of 0 is alpha. And we know y dot at 0, which is 0. So this corresponds to the initial displacement of the mass. This corresponds to the initial speed of the mass. We can now rearrange this as y of s minus s alpha. And this term here is 0 plus k ys equals to 0. Any questions so far? Any questions so far?
Just one quick small question. The s squared, like, and if you look at the line above, is that what equation is that? Like what on the formula sheet is it?
Yeah, that is not on the formula sheet. That you have to go to this slide here.
Oh, okay.
Yeah.
All right, that makes sense.
So
Thank you.
so what I'm doing there is for every derivative is multiplied by s. So d n of f of t dt to the power of n is s to the power of n f of s plus or minus the initial conditions, of course.
Oh, will the formulas be like, will we have it on a formula sheet on like the test or an exam?
Yes, you will be able to make your own formula sheet. You can write anything you want in it, but you can always use the table of Laplace transforms.
All right, thank you.
Any other questions? No? Okay. Now this is simple. You see the derivative is gone. We only have functions of s, and that is exactly what we wanted, because now we can manipulate everything and find an expression for y of t by first isolating for y of s. So let's keep y of s here on this side. That is ms squared plus k And moving to the other side, anything that it doesn't have y, that is simply this term m times s alpha. Don't forget m here. So there's going to be ms alpha. We can find an expression for y of s now, that is ms alpha divided by m squared plus k. If you look at the table of Laplace transforms, s is always multiplied by 1. So we can divide the top and the bottom of the equation by 1 over m. And this is alpha over times s squared plus k over m. This alpha here doesn't look like alpha, it looks like a fish or something. Alpha, which is a constant, right? And you see now we are pretty much done because you have an expression for y of s. It's simply a function of these s's and these two constants. Now we need to do the inverse Laplace to find the y of t. So if you want y of t, find the inverse Laplace of y of s, that is going to be y of t. And the inverse Laplace of that. Now let's go back to the table and tell me which expression here, which property can we use to solve for what we have on the board. We have s divided by s squared plus a constant. Which one is that? That is clearly number 8. Number 8, cosine of, let me write here, cosine of AT equals to s over s squared plus a squared. Right, that's number 8 in the table. Cosine of AT equals to s over s squared plus a. And you see, this is exactly what we have. We have s on top. We have s squared multiplied by 1, multiplied by 1. Very good. And we have a squared and a constant here and a constant there. What is the value of a? What is the value of a? Well, this term corresponds to that term. A squared equals to k over m. A is square root of k over m. So tell me what the result here of y of t is. Anybody?
Alpha cos root k over m times t.
Times k over cosine.
Yeah, cos
Cosine
and root of k over m
times
t.
Excellent. Very good. Here we go. Here is the time response of y of t. So it looks like a periodic sine wave. If you plot this, you would have something going from negative. So this is time, this is y of t. And if you plot this, we should get something that goes, cosine of 0 is 1, right? Yeah, so it should be something like this, going from alpha to negative alpha. Does this make sense? Well, let's look at our system. We stretch the spring, we create a potential energy in the spring, and then you let it go. The energy is transferred to kinetic energy because the mass now goes back. As the mass goes back, it will again stretch the spring, potential energy again, and then back to kinetic energy. There is no friction. There is nothing dissipating energy. So once we let the mass go from alpha 0 for alpha, it will always oscillate back and forth. It never stops because there is no friction anywhere. This is precisely what we see in here. Should we have an exponential, some damping here, another term would show up to damp out these oscillations.